try integrating it directly using this, or you could use Stokes' theorem to write it this way. You'd have to compute some partial derivatives, but you may find that the surface integral is easier to evaluate. Similarly, if you need to compute a surface integral of some vector field, and you know that it's the curl of another vector field, then you can try backtracking to this. Maybe this is easier to evaluate. So it gives you some choice. So I'm going to do one example of each type, where it's easier to work it out this way or this way. Alrighty.
Will there be a general rule that can kind of sway us in one direction or the other? Or is it
Actually, in certain cases, yes, because look at this way. Suppose you're given the surface integral, and you're not given the curl. You're given some vector field. So we'll call this vector. We'll call it E, for instance. So suppose you're given E, and you want to compute surface integral over this surface. In order to backtrack this way, you have to know that E is a curl of some vector field. Now, you might be able to backtrack and get it. In some cases, you can do that, but yeah. Usually it's applied going this way. You're given this to evaluate. You find it too hard, so you go over here, and then you just go ahead and compute the curl and go. The nice thing is certain partial derivatives that are involved in the curl, they might turn out to be 0. And I can simplify things for you. Okay. All right. Okay. A couple examples. Okay, so we have vector field F, YZ, XZ, XY, and then S is a paraboloid. Z is equal to 9 minus x squared minus y squared. So it's a downward facing paraboloid with a peak here at the point x is 0, y is 0, and z is 9. Okay. But you only take a portion of a paraboloid down to this part, down to this point where z is equal to 5. So it's all of this. This is your surface. Okay. All right. Now, you might think, okay, now I got to go to trouble parameterizing this surface and computing the surface integral, because you want to compute surface integral over S of f dot n ds, where this is going to be a unit normal n. Right. And you might think, well, that's going to be a bit of a pain, because you got to come up with parameterization of a surface, compute the normal, taking a cross product, and so forth. But alternatively, look at the boundary. The boundary of a paraboloid is just this curve here, where z is equal to 5. If we plug in z is equal to 5 right here, then it's just a curve x squared plus y squared is equal to 4. So the boundary of this paraboloid is just a circle, which is very easy to express. So So it's tempting to think, well, let's compute the integral, a line integral over this circle instead of bothering with this surface. But the trouble is, we have this relationship, curl G is equal to F. But it's G, excuse me, that we need. All right. All right. Okay. Wait a minute. I goofed here. I think I misidentified vector fields. Okay. Oh, right. Sorry. Example actually asks for to be a surface integral of curl F. So then this is F. Okay. Sorry, I made the example more complicated than it needed to be. All right. So you don't have to go hunting for this field; you already have it. Or you could have computed the curl of this and integrate that over a surface. All right. So the parameterization to use for a circle is R of t, which is 2 cosine t, 2 sine t for y coordinate, and 5, because z is just a constant 5. So now you need a tangent vector. So that would be minus 2 sine t, 2 cosine t, and 0. And t runs between 0 and 2 pi. Now you're ready to set up the integral over a curve. It's the integral from 0 to 2 pi. And now you're going to take this vector field, yz, xz, xy, with x, y, and z plugged in. So y times z, that's going to be 10 sine t. X times z, that's going to be 10 cosine t. And then x times y, that's going to be 4 cosine t sine t. Dot product with the tangent vector, minus 2 sine t, 2 cosine t, and 0. dt. All right. So now the line integral is set up. So this is, right here, your f of r of t. This is your r prime of t that you're taking a dot product with. So now you'll compute the dot product, and you get the integral from 0 to 2 pi. We're going to have minus 20 cosine sine plus 20 cosine sine. Oh, sorry, that's not right. Sorry, that's a sine, that's a cosine. So I just copied the derivatives from here. So we have minus 20 sine squared t plus 20 cosine squared t. And then here, this last part of the dot product is 0. So we get dt. Now, we can use the identity cosine squared t minus sine squared t is equal to cosine of 2t. So that's one of the double angle formulas. So now we have the integral